So I've got 3 more of these that we're going to analyze and see if we can come up with the structures. First, we have the formula, and we need to figure out the hydrogen deficiency index. In this case, it's going to be equal to 4. That's highly suggestive that we have an aromatic ring. The protons that would be on our aromatic ring are here, and there are only 4 of them. And you notice that they're in 2 doublets, so that suggests that our aromatic ring looks like this, and it's di-substituted. It has something else here and something else here. If we look over at the 9, the peak with 9 hydrogens, it's a singlet, and that strongly indicates that that would be a T-butyl. So that's going to look like this. And each one of these will have 3 hydrogens on it. Okay, so now we've accounted for 6, 7, 8, 9, 10 carbons, and we have 10 carbons in our compound. So we've got all our carbons accounted for. Let's put this T-butyl group right here. And then we have something else that comes off the other end of our aromatic. We've not done anything with our oxygen, and we have 1 hydrogen that hasn't been placed. So we're going to make this, say this is an alcohol, and that's our compound. So let's look at the next one. So we have a molecular formula of C4H6O2. It indicates that our hydrogen deficiency index is going to be equal to 2. So we've possibly got a ring, maybe a double bond. We've got 2 oxygens we need to consider. Okay, so we've got a triplet here, and a triplet here, and then a triplet of triplets. This indicates that we've got this structure. So we've got and I'm doing them in different colors so we can talk about them. And then there's an R group that comes off, right? It's attached to something else. We don't know what that is yet. All right. The triplet of triplets is the orange, because the orange ones are split by the green ones and by the pink ones. And then the green ones here are, or if we take that these are the green ones, they are downshifted a lot. So perhaps one of these oxygens is involved. So let's put, I'm going to replace this blue and just say that's going to be an oxygen. And that'll account for the downshifting here. On the other side, we are still minus a carbon. We don't have all our carbons. So let's put a carbon and make it a carbonyl. And then we need another degree of unsaturation, so let's make it a ring. This is going, so that this is going to look like is and that accounts for all the structures that we see here. So let's look at this last one. We've got a molecular formula of C9H10, O, which indicates that our hydrogen index, hydrogen deficiency index, is going to be equal to 5. That's highly suggestive of a ring. And so we've got these down here that are pretty low, that are probably involved with our ring. It's aromatic. And I'm going to assume that it's got an R group off of it somewhere. Now here, I guess we ought to do the integration before we get any further in this. If we do the integration, I get 1, 1.5, 1, and 1.5. Well, I can't have half protons, so let's change these up. And what we've got is a 2, what we have is 2, 3, 2, and 3. I couldn't get them to erase, but we'll persevere anyway. This 2 and 3, this is a quartet, and this is a triplet, highly suggestive of this structure. The 3 protons are split by the 2 protons, and the 2 protons are split by the 3 protons. So now we've accounted for 6, 7, 8 of our carbons. We still have another carbon that hasn't been accounted for, and we need to deal with the oxygen. Haven't done anything with that. So that last carbon, let's assume that it's going to be a carbonyl with something off of it. So let's put all of these together. And so we'll get our ring, get our carbonyl, and then we'll get our other 2 carbons. And if you check, that will fit all the criteria.